All right, so this lecture over 14.2 goes over Hooke's law and the idea that if an object oscillates about equilibrium with a linear restoring force, right, that object is in simple harmonic motion. So that's really what we're looking at here with this lecture. And so we're going to start with a mass oscillating on a horizontal mass on a spring and show that that is simple harmonic motion. Then we're going to compare that to a vertical mass on a spring and see if that also qualifies as simple harmonic motion. And then finally, we'll look at a pendulum and see if this qualifies as simple harmonic motion. You can see that the writing in my notes, I had answers in there. So some of that still stayed behind, but that's okay. It's not perfect, and that's fine. So it starts off here saying to define a linear restoring force. A linear restoring force is the net force directed towards equilibrium and is proportional to the distance from equilibrium. So there's kind of two key ideas here with this linear restoring force. One is that it's restoring. So it is a net force directed toward equilibrium. It restores to equilibrium. And the other is that it's linear. The linear part of it is that the force is proportional to the distance. So the further the mass, say, is moved away from equilibrium, the greater that distance, the greater the force back. You double the distance, you double the force. So we're saying that the force is proportional to the distance. So that's what we mean by linear. Okay. Let's go ahead then and look at Hooke's law. So in the textbook, Hooke's law is written as force spring equals negative kx, right? Where the negative sign reminds us the force is restoring. But on the AP sheet, they like to write it as force spring equals kx. And I kind of like the second way a little bit better, because a lot of times we'll apply the negative sign if the force points in the negative direction. So we won't need to be reminded that it's restoring, right? The negative sign, these are really the same equation. The negative sign in the first one just tells you it's restoring. So K is the spring constant that relates these two values. Kind of the idea that, whoops, I was looking for my highlighter. Let's see if I can try that again. The idea that the force spring is proportional to the distance, right? And that K is the proportionality constant. So K is going to stay constant. Yeah, and so I can make a note there, proportionality constant. And that's why force spring and distance are proportional. So K is also called the spring constant. A stiffer spring has a larger spring constant. That's important to remember. Larger spring constant, or K. Okay. All right then. Let's go ahead and head down here. Here we have a horizontal mass on a spring, and you can see it's attached to a wall. We've labeled equilibrium here with a dotted line going through the center of the mass. We are then going to displace the mass a distance x from equilibrium. Right here you can see that distance to the right. And the mass is going to experience a force to the left, back towards equilibrium is the idea. Here we see mu is 0, so that means no friction. Mu is the coefficient of friction, and so that means when there's no mu, there is no frictional force. Our formula for mu is force friction is equal to mu Fn, right? And so just something to keep in mind. If mu is 0, then force friction is 0. Okay, if the mass is then displaced a distance x to the right of equilibrium, use Newton's second law in the x direction to find the net force in the x direction. So just like we said, this net force is going to be back to the left. Let's go ahead and solve for it, right? So if we look at this down here, we see that we have the sum of the force in the x direction is equal to max. We can then rewrite this as F net in the x direction is equal to the force spring. But since the force spring is going to be restoring, right? If I go back over here, I can go ahead and add this in. Let me go ahead and pick blue here and say that the force spring points just like this. And notice it points towards equilibrium. So since it's negative, we'll call that negative force spring. And that's equal to max. We're actually just going to use this first part. So let's go ahead and rewrite this again. We can say that F net in the x direction is equal to negative, and force spring, as we set up here, force spring equals kx. We aren't going to use the top one because the negative sign is already on there for us. It's already applied. And so we'll just write this as kx. We can then go ahead and write out F net in the x direction is negative kx. And so what we see here, this is similar to Hooke's law, and we can see that it is the net force is a linear restoring force, right? Because we move the object to the right, and force spring points in the negative direction, or the net force points in the negative direction, and the two are proportional because k is constant. So because k is constant, F net in the x direction is proportional to x. So therefore, we can say that a mass on a horizontal spring has a net force that is a linear restoring force. And therefore, you can say it oscillates in simple harmonic motion. Okay. So what we want to know now is, what about a mass on a vertical spring? And what about a pendulum, right? Will it have the same relationship with the net force? a linear restoring force, and that's what we want to know. So let's go ahead and look at that. Here we have, on the next page here, 2 parts. So we're going to do the part on the left first, part 1, and then part 2 over on the right. I think you can see that. Let me go ahead and underline it really quick. Let me try a red highlighter. Let's see how this works. So here's part 1, and then over here in red, this will be part 2. So we'll tackle part 1, or the left side of the page first. So what we have here, and it says up here, the equilibrium position of the block is not where the spring is at its unstretched length. Okay, so what we have down here is 2 equilibrium positions that we're going to think about. And this is confusing, so we want to be able to clarify which one is important here, right? But to do that, we're going to go ahead and go through and solve and look at what's actually happening. We have the old equilibrium position, which is just the unstretched spring. It's just hanging out. It's attached to the red ceiling that I've underlined there, highlighted. And it's not doing anything in this position right here. I don't have a dotted line here, but I could make a dotted line if you like. Is the old equilibrium position. And this new equilibrium position, which I'm going to refer to as 0, because you can see the 0 hanging out right here. Is down here when I hang a mass on the spring and not drop it, right? I pretty much just let the mass fall to wherever it feels like it stops and just leave it there, right? So the mass is just hanging there. It's not oscillating. It's not bouncing up and down, oscillating, or moving back and forth about equilibrium. It's not doing anything. It's just sitting there. And you can see I drew a dot here. Usually I like to draw this in the center, but for some reason I drew it to the side slightly. Okay, so the first thing says to draw a free body diagram for new equilibrium. And that Hooke's law states what? Okay, so let's go up here and draw the free body diagram first. And let's go ahead. Maybe I'll pick blue here again. It seems to be working all right. So we have the force of the spring pointed up. We have force gravity pointed down. And we know these are going to be equal and opposite because the net force is 0 on this object, right? We know that for a fact. It's just sitting there and it's not doing anything. It's not accelerating. And if there was a net force, there would be a net acceleration, and there isn't. All right, we'll call this distance here from old equilibrium down to here. We'll call this distance delta y. Or delta L, sorry. All right, delta L maybe for change in length or something along those lines. All right. So, so I guess we're kind of maybe calling old equilibrium 0 then in a way, because this is now at position delta L. So maybe old equilibrium is the 0 point. Maybe my 0 here is incorrect. All right, let's go ahead and move down. Draw a free body diagram for new equilibrium. Okay, so Hooke's law states what? All right, Hooke's law states that the force of the spring is equal to kx. And here we're working in the y direction. And so the displacement from old equilibrium is delta L, right? So let's go ahead and write that in down here. Okay, and delta looks kind of funky, but you get the idea. That's a triangle. All right, delta L. Okay, ignore the negative sign because force spring. Okay, so yeah, we're not putting a negative sign on Hooke's law because force spring does point up, and we are calling up positive, right? And we are calling down negative. So that's kind of the idea here. All right, Newton's second law in the y direction. So we can then sigma our forces in the y direction. This is the same as us writing F net in the y direction. Is equal to MAY. And we know that this is equal to 0 because we just said a second ago that AY is equal to 0. All right. The acceleration is 0. So I'm going to go ahead and write that for my sigma y forces. For my sigma y forces, let me stick with blue. All right, so what I'm trying to say is I am not going to work with the F net y part of that. I'm just going to stay with, let me highlight. I'm just going to stay with that part of it right there. Because I don't need all three equalities, right? I just need the two. Forces coming up here. Force spring acts up, force gravity acts down. So we're going to have force spring minus force gravity down here. Equal to the mass times 0 acceleration, right? Which we know is going to be just 0. Force spring is going to equal, as we said, K delta L. Fg is always mg on the planet Earth. And we can then go ahead and kick mg over to the other side and divide by K. So I'm going to go ahead and do that a little bit slow. Just like that. Divide both sides by K. Whoops. And we can solve for delta L. I'm going to go ahead and write it right under here. Delta L is how far the spring stretches when the block is attached to it. And so now we have an expression for delta L. Now you might say, well, why we need that? Well, it's going to come in handy here in a second. Because what we're going to do is we're going to analyze the net force that occurs on this block when the object is displaced from equilibrium. So if we come up to part 2 up here, we and maybe I'll try and zoom out for a second. What's going to happen here is we're going to move this mass. Let me maybe give it some color. So this mass here in orange, which was just hanging out at its new equilibrium, is now going to be displaced upward. Now, this distance it's displaced upwards is going to equal y. It's going to be shifted up a distance y. So you can see that right here. That's the distance from new equilibrium, right? Because new equilibrium, you can just extend it across the page. It's right here. You can see I'm extending across. So y is this distance that it's going to be displaced. But if we think about how far the mass is from old equilibrium, which is kind of tricky to think about, but from old equilibrium, it is, if this is delta L, let me highlight it really quick. If this is still delta L over here, you can see that, then the distance that this is right here, let me highlight this in pink maybe. This distance here is delta L minus y. That's what I'm trying to say right there. Because delta L is all the way to from old equilibrium to new equilibrium, and now it's been lifted up a little bit, so it's not delta L anymore, it's smaller, so it's delta L minus y. And so that's what that pink distance is there. So that we're going to need to think about that too. So the spring is, I guess it's kind of getting at the idea that the spring is still stretched downward, right? And so let's go ahead and add that in. And we mean downward from old equilibrium. Yeah, and they tell us that compared to old equilibrium. Therefore, the spring still pulls upward. This is confusing thinking about old and new equilibrium. So hopefully we can come to some conclusion at the end here that helps with that. Draw the free body diagram above. F net points towards new equilibrium or down. Okay, so what we have here then is, if we think about this, right? force gravity is going to be the exact same size as before. And you drew it over here on the left, so I'm going to redraw it the same exact length as before. But now the force spring was pulling harder here because it wanted to get all the way back to old equilibrium, which was a distance delta L away. Here, the mass is now higher up, so the distance away is delta L minus y, right? The pink distance from old equilibrium. So therefore, the force spring doesn't pull as hard, right? Because it's not as far, it's not displaced as far. So it's going to pull with less force, this force spring that points upwards. So I'm going to go ahead and draw this maybe in, I'll draw it as pink, I guess. All right, so now we can just look at the forces and say, well, the downward force is larger than the upwards force, so therefore the net force is going to point downwards. And that's what we're seeing, is that the net force is pointing us back towards new equilibrium. Okay, so that's interesting. It's kind of getting an idea that maybe new equilibrium is what is important here, right? All right, so okay, so we have the spring still pointed upwards as we see with the pink force, albeit smaller. Draw the free body diagram above. F net points towards new equilibrium or down. Okay. The spring force is different because it is now stretched delta L minus y, right? It's not delta L anymore, it's not as large. From old equilibrium, use Hooke's law to calculate the new force spring. Okay, force spring, Hooke's law states, is equal to kx. We can then say that force spring is equal to k times delta L minus y. Because remember, the block was lifted a distance y. All right, but this is the distance from where the block is to old equilibrium. Okay, so which way does force spring point? Okay, we already said force spring is going to point up. Okay, good, good. Let's go ahead and move to the next page. All right, so here we have Newton's second law in the y direction. So we can go ahead and sum our forces. And this time, we're not going to be able to say that the acceleration is equal to 0, right? The acceleration is actually going to be some negative number, right? It's going to point downwards. Because remember, the acceleration points in the same direction as the net force. And the net force here was downwards, right, towards new equilibrium. All right, so coming back to this then, we can say the force net is equal to force spring, which points upwards, minus force gravity, right, just like before. But here's where it gets a little tricky, right, because our distance now is not delta L, but it's delta L minus y that the force spring operates off of, because it's trying to return back to, it's pointing up because it's trying to return back to old equilibrium. And then we have minus mg. All right, and we know this mg is larger than k delta L minus y. Okay. So let's just go ahead and keep writing this because it's probably wise to. Here we can actually take advantage of something here with this delta L. Whoops, it's kind of bright there. Let me stick with yellow maybe. Okay, so we need an expression for delta L. And so now it makes sense. If we go, where was it? Oh, it was just down here. All right, I went a little too far. Delta L equals mg over k. And so you can see now why in the previous part, in part 1, we wanted to find an expression for delta L. All right, that was kind of the idea. And once again, if I'm losing you, this is all covered in your textbook, but you might just have to go back and watch it one more time, and it should make sense. So we're just going to go ahead and bring that, let's see, it's kind of an awkward way to draw that line, but yeah, down there to there. And we can go ahead and write mg over k. All right. Okay, then we can go ahead and distribute this k through. I'm going to show you what I mean. So this k is going to go there and there. All right. Do a little canceling. And that is very nice right there, because now we can see we can simply cancel off the mg's. And what this is showing is that the force of gravity doesn't matter, right? And we're going to be left with a linear restoring force. And this is the same, if you think about it, this is the same as if the mass was oscillating on a horizontal surface without friction, right? It's the same exact thing. So a mass on a vertical spring oscillates with a linear restoring force and is therefore simple harmonic motion. So let's go ahead and write that down. And we should probably specify which equilibrium. It's going to be oscillating about new equilibrium. All right, good. So therefore, you can ignore the effect of forced gravity for a mass on a vertical spring. So what is gravity's role then? A couple things. Determine where new equilibrium is. Well, that's really it. And that's kind of the idea that when we displaced it a distance from new equilibrium, gravity doesn't affect the restoring force. So maybe instead of saying it, be a little more specific here. All right, good. So Fg does not affect the restoring force for displacement from new equilibrium. It's just like force gravity didn't affect this mass on a horizontal spring, right, that we looked at right here. Force gravity also does not affect the mass on a vertical spring, although it's much harder to see why. Obviously, we do that giant derivation. But gravity's role is just to find new equilibrium, right? And then once you find it, the mass will oscillate with a linear restoring force in simple harmonic motion about new equilibrium. That is what we're saying. All right, cool. What about the pendulum, right? Does the pendulum have a linear restoring force similar to a vertical mass or a horizontal mass right here? Can a pendulum be described the same way, right? And so let's go ahead and look at that. Okay, so is the restoring force linear? If so, the motion is simple harmonic. A pendulum's position, we're going to call 0 when the pendulum is hanging straight down. So here, what we have in this picture here is a pendulum that has been displaced to the right from straight down. And since moving to the right is counterclockwise, and counterclockwise rotational motion was positive, we're going to call it right positive and left negative. So we expect there to be a restoring force pointed back to the left, back towards equilibrium, or back in the negative direction for this mass right here, right? That's what we're talking about. Okay, so if so, the motion is okay. Pendulum position, 0 when hanging straight down, described by either, well, we can describe it two ways. We can describe it by the angle or the arc length. So let's go ahead and write that in, either by the angle theta or the arc length. I feel like, is arc length one word? I think it might be. Can't remember. Or the arc length, which we're going to call S. All right. Good. And we already said if S is to the arc length is to the right, we'll call it positive, and if the angle is to the right, we'll call it positive, and we already stated that. Okay, so what we got to do is look at this restoring force, and we're kind of interested in a tangential force. So these little t's I have written here, F net tangential equals sigma F tangential equals Fg tangential, is all about a tangential force. So let's go down here and look at this. So what we have here, if we think about this in free body diagram, this green object hanging on a purple string here, which I'm going to draw. And we have the ceiling up here, which we can make, I don't know, I highlighted it red last time, so let's just stick with that. So there's the ceiling. And we have two forces acting on the pendulum. And we'll draw them acting from the bob or the mass. And so what are the two forces? Well, let me go ahead and draw one of them. One points just like this from the string, and so we can call that one tension. And the other one points straight down, just like this, and we can call that one force gravity. All right, and then that's it, right? Those two forces. But we know that that these forces, we have to get them to agree with a coordinate system. So we're actually going to use a coordinate system that points straight up and down like this, and then left and right like this. And the idea here with this is that the x direction will be the tangential direction. And and the y direction will balance out the tension. So we're going to split force gravity into its components in this new axis, coordinate axis system. So here, this is the part of force gravity which we can call FGY. And this is going to be the part that's going to be FGX, which I can label right here if you like. But I also already labeled it right here. Right. So I have it acting up there from the bob. I'm gonna leave it in both places right now, which hopefully isn't confusing. This is going to create a 90-degree right angle right here. That means that FG is our hypotenuse, and FG is, of course, MG. We then know that we can see, hopefully, similar triangles here. If we look, we can see the angle theta is this angle right here. So because of that, we can go ahead and use a little SOHCAHTOA here and say this is the adjacent. So therefore, this is equal to the hip cosine theta. So mg is the hip times the cosine theta. Once again, you should write that out if you can't remember how to do that, but I guess I can do it too if you like. This is equal to mg sine theta. All right, because this is my opposite. All right, so this is my force gravity tangential, by the way, and so I call it FGT. So yeah, what did I? So hopefully all of the SOHCAHTOA is making sense. I can do it really quick, I guess. The ka part for the cosine, right? So we had equals the adjacent, which is FG. We said that's FGY. And we know FG is MG. All right, so hopefully that's making sense. By that same logic, you can say sine theta is equal to FGX over FG, because sine theta is equal to op over hip. And so you can then say sine theta whoops, I mixed up. Trying to go too fast. And then we can go ahead and say FGX equals mg sine theta. All right. Yeah, you don't want to make mistakes doing that stuff, and you got to remember how to do it because it's important for the AP test. Okay, so coming back to this then, what can we say? Before we write anything down here in this box, I actually want to bring this back up here. So we should remember that this mg or FGX or FG tangential does point to the left. So this is going to be negative mg sine theta when I bring it up here because it points left. And you can see I already made that notation on the page. All right, negative mg sine theta for FG tangential. All right, points clockwise, which is negative. All right, because it points towards equilibrium, and because you can kind of see where this is going, I think. All right, now an interesting thing happens when you take the sine in radians for angles of 10 degrees or less. 10 degrees, just in case you're wondering, is about 0.17 radians. Now, when you take the sine of 0.17 radians, you get 0.17 radians. So it's like you didn't even do anything. So what we can say then is this relationship right here, right? That the sine theta is approximately theta for angles of 0.17 radians or less. Now, this does not work with angles 10 degrees and less when you sine them in degrees. You have to have it in radians. And so this is called the small angle approximation. Applies only in radians, like I just said. Okay. So why not in degrees too? I don't know. I can't answer that. I'm not sure. But this is how this works. So if we remember something from rotational motion earlier in the year, is that if you multiply the angle theta in radians by the radius, you get S, which is the arc length, right? We had these three relationships. One was that one. One was omega times theta is equal to velocity, and one was alpha. I'm sorry. Let me make that again. Multiply by the radius. One was omega times the radius is equal to velocity. One was alpha times the radius is equal to the acceleration. And so this was the first one right here, which is that theta, right, angular position multiplied by the radius is equal to S, or the arc length. So we had a way to go from rotational motion into linear motion. And so that's what we have right here. Let's just rearrange then and solve for theta. Divide both sides by r. So we can say S over r is equal to theta. Now, I wrote over here that theta equals S over L. This is because in this problem and the book, they call the length of the pendulum L, which it is. So so we'll just make that substitution here and go we can work off that, because we do like to refer to the length of a pendulum as L. So L equals the length of pendulum. And here we're saying R is equal to L. And so that's why. So we have an expression now for theta. Okay, interesting. So what we can then say, if we come down here, is that go ahead and use this expression for theta, right? We'll go ahead and say F net tangential, which is negative mg sine theta, then is negative mg sine of S over L. But for small angles only, right, in radians, we can go ahead and make get rid of sine, right? Because the sine of S over L is just S over L. So it doesn't matter. So we can say here that this net tangential force back towards equilibrium pointed to the left, this FGT, right, force gravity tangential, is equal to, and I guess it is the net tangential force, yeah, FGY and tension are going to balance out, so it's really just the net force altogether, but whatever. We have down here the negative mg S over L. All right, so true at small angles only, and that's what we have to remember here. Okay, so let's bring it back home. Let's talk about, is this a linear restoring force, right? That's kind of what we're getting at. Okay, so let's just make a quick, let's rewrite this in a slightly different way. So we'll write F net tangential. Whoops, I'm in my highlighter. Is equal to, I'm just going to rearrange it slightly. Still negative mg, and I'm just going to bring the L in right here and leave S outside. And what you can see we have here is we have a constant, let me see, right here, that this is our constant, that the mass isn't changing, gravity isn't changing, the length of the pendulum isn't changing. So what we have here is a constant like K, like the spring constant, that is a proportionality constant between, check it out, right? Whoa, every time I go for that highlighter, I get the marker instead sometimes. Between the force net tangential, or the net force, and the arc length, which is the distance the sphere is displaced along that circle, right? So we can see that this is a linear restoring force, right? It's also linear. You can think about it in the form of y equals mx, right? Where you could graph y versus x, and the slope would be k, or the slope would be mg over L, or the slope would be m. The negative sign, I guess, doesn't even have to, if you're like, well, what about the negative sign? I guess I could have, let me see, I could have wrote the negative sign out here, right? And then therefore you have your mg over L as your constant, and the negative is just showing you that it's restoring, it's going back towards equilibrium, right? If you would have pulled the pendulum the other direction, then it would be a positive sign out there, so it's not a big deal. Just going to send it back towards equilibrium. So what that means is, let's go ahead and kind of summarize here. There is a linear restoring force for pendulums at small angles from equilibrium. And they do oscillate in simple harmonic motion at these small displacements. All right. So once again, another linear restoring force, similar to force spring equals kx, right? Or force spring equals negative kx, whatever you want to call it. And it's true for pendulums at small angles. All right, so there you have it, proof of why pendulums operate according to a linear restoring force and at small angles and operate in simple harmonic motion. Proof of why vertical springs, right? Vertical springs operate with a linear restoring force and move in simple harmonic motion, exactly the same as a horizontal pendulum, and so exactly the same as this, right? Look at the equation; it's very similar. And right, and a linear restoring force, and anytime you have a linear restoring force for an object oscillating about equilibrium, you have simple harmonic motion. Simple harmonic motion we're going to see in the next section is sinusoidal. So therefore, we can represent it with cosine and sine waves. All right. So that's it. Hopefully this is making sense, and have a good day.